is improving, and hopefully we're expecting something a bit more reasonable. Okay, so we're down at about 2.5-ish. Let's see what we get. Okay.
I'm getting 4.69. I want to improve this. Let it run again 10,000 times more. I won't initialize it. I will just train the model again and try to predict.
A dramatic improvement certainly on what we had here.
Hopefully we'll
So
get output
let me
like
just
this.
increase the number of tokens. Okay, so we see that we're starting to get something at least like reasonable-ish. Certainly not Shakespeare, but the model is making progress. So that is the simplest possible model. So now what I'd like to do is, obviously this is a very simple model because the tokens are not talking to each other. So given the previous context of whatever was generated, we're only looking at the very last character to make the predictions about what comes next. So now
Still, I'm getting pretty bad output. Let me print the loss. It's hovering around the same.
simply not. So we see that
One thing.
this way. So just a quick comment on that. So now we see that this is random. So let's train the model so it becomes a bit less random. Okay, let's now train the model. So first what I'm going to do is I'm going to create a PyTorch W. Now in the makemore series, we've only ever used stochastic gradient descent, the simplest possible optimizer, which you can get using the SGD instead. But I want to use Atom, which is a much more advanced and popular optimizer, and it works extremely well. For typical good setting for the learning rate is roughly 3e-4, but for very, very small networks, like is the case here, you can get away with much, much higher learning rates, 1e-3 or even higher probably. But let me create the optimizer object, which will basically take the gradients. Our batch size up above was only 4, so let me actually use something bigger, let's say 32. And then for some number of steps, we are sampling a new batch of data, we're evaluating the loss, we're zeroing out all the gradients from the previous step, getting the gradients for all the parameters, and then using those gradients to update our parameters. So a typical training loop as we saw in the makemore series. So let me now, so we started around 4.7, and now we're getting down to like 4.6, 4.5, etc. So the optimization is definitely happening, but let's sort of train for longer. Okay, so we're down to 3.6 roughly.
I have given 10,000, but still I don't see. So when we write vocab size, vocab size. So it does a prediction all. To cross 65 and then what that used to do, really sorry. Um, I just want to see. So 1 cross 65 because we are sending it just the initial that thing. So that's a 1 cross 65 metric that we are generating there. Then we're doing a softmax, making a prediction. Equal to 1, yeah, looks all fine to me. Check. Okay. No, but that anyway should not affect that, right? We're just generating. Yeah. What happens when I do a -1? Not very sure. It's 1 cross 65 itself, right? Oh, okay. Anyway, nothing much changes here. Out of those 65, we are pulling in 1 and we are feeding it to here, and that is the IDX, and that's what is getting returned. Looks all good to me. For him also it's coming like this, no? But this is with 100. Okay. Optimizer is fine. XBYB is fine, right? XB is for whole of this. It gets downloaded here. I open read, print, characters, all the text. Encoding is done. I encode the complete text. Okay, text. So that is also done. There are 11,50,000 first initial few characters. Training and validation so that we can this was, I think, to print that. 2 many indices, so tensor of dimension 1 yx. Oh, this is just for printing, right? This is a whole example in itself. Let's see. And then we'll try to generate it. Okay, anyway, we'll proceed further. We'll see.
Okay, so next, I took the code that we developed in this Jupyter notebook and I converted it to be a script. And I'm doing this because I just want to simplify our intermediate work into just the final product that we have at this point. So in the top here, I put all the hyperparameters that we've defined. I introduced a few, and I'm going to speak to that in a little bit. Otherwise, a lot of this should be recognizable. Reproducibility, read data, get the encoder and the decoder, create the train and test splits, use the kind of like data loader that gets a batch of the inputs and targets. This is new, and I'll talk about it in a second. Now, this is the bigram language model that we developed, and it can forward.
Sorry. That's running clock. Let's see if any improvement we see here.
And give us a logits and loss, and it can generate. And then here we are creating the optimizer, and this is the training loop. So everything here should look pretty familiar. Now, some of the small things that I added. Number one, I added the ability to run on a GPU if you have it. So if you have a GPU, then this will use CUDA instead of just CPU, and everything will be a lot more faster. Now, when device becomes CUDA, then we need to make sure that when we load the data, we move it to device. When we create the model, we want to move the model parameters to device. So as an example, here we have the NN embedding table, and it's got a .weight inside it, which stores the sort of lookup table. So that would be moved to the GPU, so that all the calculations here happen on the GPU, and they can be a lot faster. To the GPU inside it, which stores the sort of NN embedding table, and it's got a .weight inside it, which stores the sort of lookup table. So that would be moved to the GPU, so that all the calculations here happen on the GPU, and they can be a lot faster. And then finally here, when I'm creating the context that feeds into generate, I have to make sure that I create it on the device. Number two, what I introduced is the fact that here in the training loop, here I was just printing the loss.item inside the training loop. But this is a very noisy measurement of the current loss because every batch will be more or less lucky. And so what I want to do usually is I have an estimate loss function, and the estimate loss basically then goes up here, and it averages up the loss over multiple batches. So in particular, we're going to iterate eval iter times, and we're going to basically get our loss, and then we're going to get the average loss for both splits. And so this will be a lot less noisy. So here, when we call the estimate loss, we're going to report the pretty accurate train and validation loss. Now, when we come back up, you'll notice a few things here. I'm setting the model to evaluation phase, and down here, I'm resetting it back to training phase. Now, right now for our model as is, this doesn't actually do anything, because the only thing inside this model is this nn.embedding, and this network would behave the same in both evaluation mode and training mode. We have no dropout layers, we have no batch norm layers, etc. But it is a good practice to think through what mode your neural network is in, because some layers will have different behavior at inference time or training time. And there's also this context manager, torch.nograd, and this is just telling PyTorch that everything that happens inside this function we will not call that back.
This loss is with respect to patch, right? How come when we call get batch? Okay, it takes that as well. Hmm, okay. So this loss that we are seeing, right, is per batch. That's why it's very noisy. That's what he was saying, right? Because every batch, uh, we're taking explicitly training it and getting it, but overall result, right? What we should get should be a good one, is something I believe. So there is no point running it for a 1 lakh time. But anyway, let's see. Let it generate the output.
Backward on. And so PyTorch can be a lot more efficient with its memory use because it doesn't have to store all the intermediate variables because we're never going to call backward. And so it can be a lot more memory efficient in that way. So also a good practice to tell PyTorch when we don't intend to do backpropagation. So right now this script is about 120 lines of code and that's kind of our starter code. I'm calling it bigram.py and I'm going to release it later. Now running this script gives us output in the terminal, and it looks something like this. It basically, as I ran this code, it was giving me the train loss and the val loss, and we see that we convert to somewhere around 2.5 with the bigram model. And then here's the sample that we produced at the end. And so we have everything packaged up in the script, and we're in a good position now to iterate on this. Okay, so we are almost ready to start writing our very first self-attention block for processing these tokens. Now, before we actually get there, I want to get you used to a mathematical trick that is used in the self-attention inside a transformer, and is really just like at the heart of an efficient implementation of self-attention. And so I want to work with this toy example to just get you used to this operation, and then it's going to make it much more clear once we actually get to it in the script again. So let's create a b by t by c, where b, t, and c are just 4, 8, and 2 in this toy example. And these are basically channels, and we have batches, and we have the time component, and we have some information at each point in the sequence, so C. Now, what we would like to do is we would like these tokens, so we have up to 8 tokens here in a batch, and these 8 tokens are currently not talking to each other, and we would like them to talk to each other. We'd like to couple them. And in particular, we want to couple them in a very specific way. So the token, for example, at the 5th location, it should not communicate with tokens in the 6th, 7th, and 8th location, because those are future tokens in the sequence. The token on the 5th location should only talk to the one in the 4th, 3rd, 2nd, and 1st. So information only flows from previous context to the current time step. And we cannot get any information from the future because we are about to try to predict the future. So what is the easiest way for tokens to communicate? Okay, the easiest way I would say is, okay, if we're a 5th token and I'd like to communicate with my past, the simplest way we can do that is to just do an average of all the preceding elements. So for example, if I'm the 5th token, I would like to take the channels that make up that are information at my step, but then also the channels from the 4th step, 3rd step, 2nd step, and the 1st step. I'd like to average those up, and then that would become sort of like a feature vector that summarizes me in the context of my history. Now, of course, just doing a sum or like an average is an extremely weak form of interaction. Like this communication is extremely lossy. We've lost a ton of information about the spatial arrangements of all those tokens. But that's okay for now. We'll see how we can bring that information back later. For now, what we would like to do is, for every single batch element independently, for every teeth token in that sequence, we'd like to now calculate the average of all the vectors in all the previous tokens and also at this token. So let's write that out. I have a small snippet here, and instead of just fumbling around, let me just copy paste it and talk to it.
So for each batch, for each batch, D what is capital D here? Okay. So for every tth position, we have the average as well. Okay. It's somehow not reducing. So what that is doing is, say B is 0 and T is 1. Somehow pretty bad example. Say T is 2 here. So what it will do, it will 10 plus 22 plus, take it here again, 10 is there, say 10, 20, 32, 42, and that mean it out. It's mean by 3. So it will come around 14 or something. So you will see 14 here. Okay, so that was for this t equal to 2. The same we'll calculate for t equal to 4, 5, 6, 7, like this will go ahead.
So in other words, we're going to create X, and BOW is short for bag of words, because bag of words is kind of like a term that people use when you are just averaging up things. So this is just a bag of words. Basically, there's a word stored on every one of these 8 locations, and we're doing a bag of words, so just averaging. So in the beginning, we're going to say that it's just initialized at 0, and then I'm doing a for loop here, so we're not being efficient yet. That's coming. But for now, we're just iterating over all the batch dimensions independently, iterating over time.
Still, we are getting pretty bad loss. Not very sure if I'm missing something here. Now I remember where the issue is. My model was not learning itself because I was taking the parameter of this model that I defined somewhere later down the lane. Yucks. That sucks. Hopefully, now my parameters for GC. Now we see loss coming down. That was bad. This should give a good enough result, but let me do the mathematical trick.
And then the previous tokens are at this batch dimension, and then everything up to and including the teeth token. Okay? So when we slice out x in this way, xprev becomes of shape how many t elements there were in the past, and then of course c, so all the two-dimensional information from these little tokens. So that's the previous
Looks better for sure. Also, the error has reduced. Yeah. Start manual seed 1337 comma t comma c equal to 4 comma 8 comma 2 and x equal to torch round n p comma t comma c. So x dot shape. So let me try to write this down on. Okay, so search for b in range of capital B for all range of capital B for batch. This is token for T in the range of capital T. So we have, so where we have, so say we are, say here, just for an example, B0 T is 1. We need to do average out of all these values 10, 22, 7, 19, 6, 14, 16, 4, 13, 1. Okay. Um, um, and where is that stored? All this, all those values are stored in X. Why? How come it is stored in X? What is X? Oh, okay. As for the time being, he has just taken X. So X B we need to take that is the block size T plus 1 because T will be 1, so till T plus 1 we need to take. So this will take, say, these two, this thing X on this previous X underscore previous sum across first row, right? Dim equal to 1. Okay, and that needs to be stored as well. X underscore bow equal to torch it will be of the same shape, right? B comma T comma C. Because for each token we'll get, right? For each of these token we'll get like this pillar standing. So that will be x underscore bow b t equal to the non-single. Uh, um, what is 1 or 2 here? That is 4 cross 8 cross 2, right? 0. So 1 cross 2. Oh, okay. So in the initial iteration, we are taking 0 at this thing. So we should get just this pillar, right? Because t will be 0 here. This blue thing will be 0. But it should be 1 cross 65, no? That's messing up somewhere, I believe. What is 1 cross 2? B will be 0, t plus 1, t will be 0 initially, so 0 plus 1, 1. So we're plucking out 0 with red 1, 1 blue 1, so it should be 1 cross 65. Uh, that is t cross 65, yeah, 1 cross 65. R, okay. No, it's 2 only. No, here I have said that's why it's 1 cross 2. It's not 65. That's why you are getting. So this is not 65 here. Only 2 are kept here. So this green, right? Green has only 0 and 1. Means only 2 elements are there. Okay. And what happens then? Okay, there's nothing like this formula itself. Sorry. All the other things are good. It should be torch dot mean X previous. Two cross two. 0 is the row dimension. Okay, sorry for that. Switch. So it should have the same dimensions.
Sort of chunk of tokens from my current sequence. And then I'm just doing the average or the mean over the 0th dimension. So I'm averaging out the time here. And I'm just going to get a little C one-dimensional vector, which I'm going to store in X bag of words. So I can run this, and this is not going to be very informative because, let's see, so this is X of 0. So this is the 0th batch element. And then expo at 0, now, you see how at the first location here, you see that the two are equal. And that's because we're just doing an average of this one token. But here, this one is now an average of these two. And now this one is an average of these three. And so on. So, and this last one is the average of all of these elements. So vertical average, just averaging up all the tokens, now gives this outcome here. So this is all well and good, but this is very inefficient. Now the trick is that we can be very, very efficient about doing this using matrix multiplication. So that's the mathematical trick. And let me show you what I mean. Let's work with the toy example here. Let me run it and I'll explain. I have a simple matrix here that is a 3 by 3 of all ones, a matrix B of just random numbers, and it's a 3 by 2, and a matrix C, which will be 3 by 3 multiply 3 by 2, which will give out a 3 by 2. So here we're just using matrix multiplication. So A multiply B gives us C. Okay, so how are these numbers in C achieved, right? So this number in the top left is the first row of A dot product with the first column of B. And since all the row of A right now is all just ones, then the dot product here with this column of B is just going to do a sum of this. This column. So 2 plus 6 plus 6 is 14. The element here in the output of C is also the first column here, the first row of A, multiplied now with the second column of B. So 7 plus 4 plus 5 is 16. Now you see that there's repeating elements here. So this 14 again is because this row is again all ones, and it's multiplying the first column of B. So we get 14. And this one is, and so on. So this last number here is the last row, dot product, last column. Now the trick here is the following. This is just a boring number of, it's just a boring array of all ones, but Torch has this function called trill, which is short for a triangular, something like that. And you can wrap it in torch.once, and it will just return the lower triangular portion of this. Okay. So now it will basically zero out these guys here. So we just get the lower triangular part. Well, what happens if we do that? So now we'll have A like this and B like this. And now what are we getting here in C? Well, what is this number? Well, this is the first row times the first column. And because this is zeros, these elements here are now ignored. So we just get a 2. And then this number here is the first row times the second column. And because these are zeros, they get ignored, and it's just 7. this
The
7 multiplies
second
this 1.
column we take to
But
third
look what
column.
happened here. Because this is 1 and then zeros, what ended up happening is we're just plucking out this row of B, and that's what we got.
So to get that thing, we can do what is the torch dot trail. If I just talk about a batch, okay, it will be equal to just I'm talking about a single batch. It will be the size of that, so it should be equal to T cross T rows, T columns, is it? Yep, T rows, T columns. So frill, sorry. Okay, got it. What it does, it takes this. Okay, so what it will happen when it multiplies this 8, right? Means whatever is in this 8, it multiplies this with it. It will just pluck out the first one because first one is 1. Next case 2 are 1. So it will pluck out these two. So when I multiply this, what is the shape of this individual? 8 cross 8. I'm for now I'm not considering B here, just T into C. Okay, and uh, T into C is 8 cross 2. 8 comma 2. Okay, so when the dot product happens between these two, it will become 8 cross 2. Okay, and we'll get all the sums. Yeah, so for each of those 8 we get the sum like that, and we need to do that for each of the batch. So I think it should be like this. One after the other, one after the other. Um,
Now here, we have 110.
What are the average salaries of Excel users? So basically, a normal Excel user can expect a salary of around 5 LPA. But if
Let's get it 2.
ChatGPT is open somewhere. Converting. Not sure if this can help. How many times you wanna repeat? B times A. Okay, not sure. Let's see.
And then this number here is the first row times the second multiple and 7 plus 4, which is 11. And so basically, depending on how many ones and zeros we have here, we are basically doing a sum currently of a variable number of these rows, and that gets deposited into C. So currently we're doing sums because these are ones, but we can also do average, right? And you can start to see how we could do average of the rows of B sort of in an incremental fashion. Because we don't have to, we can basically normalize these rows so that they sum to 1, and then we're going to get an average. So if we took A, and then we did A equals A divide, torch.sum in the, of A, in the
Okay.
1th dimension, and then let's keep them as true. So therefore the broadcasting will work out. So if I rerun this, you see now that these rows now sum to 1. So this row is 1, this row is 0.5, 0.5 is 0, and here we get 1/3.
Nice. Loved it. Nice.
And now when we do A multiply B, what are we getting? Here we are just getting the first row. Here now we are getting the average of the first two rows. Okay, so 2 and 6 average is 4, and 4 and 7 average is 5.5. And on the bottom, the average of all of manipulating these elements of this multiplying matrix, and then multiplying it with, because we just get, so let's swing back up here and see how we can vectorize this and make it much more efficient using what we've learned. So in particular, we are going to produce an array A, but here I'm going to call it way.
So this T cross T is doing it. Nice. Giving it as way. Way. So we
Short for
get
weights. But this is our A. And this is how much of every row we want to average up. And it's going to be an average because you can
the same we can multiply with each of that. Okay, got it. So he doesn't need to do this. So what we'll do, X is 4, 8 cross 2. We'll do a way. Okay, that is like 8 cross 8. No, but it again needs to.
see that these rows sum to 1. So this is our A. And then our B in this example, of course, is X. So what's going to happen here now is that we are going to have an expo 2. And this expo 2 is going to be way multiplying our X. So let's think this through. Way is t by t, and this is matrix multiplying in PyTorch a b by t by c, and it's giving us what shape. So PyTorch will come here and it will see that these shapes are not the same. So it will create a batch dimension here. And this is a batched matrix multiply.
Ah, okay. Okay.
And so it will apply this matrix multiplication in all the batch elements in parallel and individually. And then for each batch element, there will be a t by t multiplying t by c exactly as we had below. So this will now create
Okay. So that broadcasting if happens, right? So it is B cross T cross C. If will this work is B T C at the rate happening with what is way, that is T it yeah, so what it will do, it will add up B as well. Here is what he's saying. ECTT, it won't be able to multiply, right? This index needs to be same. So that's why this becomes Y, this becomes X, this is BTT, and this is BTC, and this is X, about 2 equal to Shack. Thoroughly impressed. Nice.
b by t by c, and expo 2 will now become identical to expo. So we can see that torch.allClose of expo and expo 2 should be true. Now, so this kind of
Finally, these two are not same as what this guy is saying. Looks similar to me. Hmm. All the elements look no idea. Since both to be same, It says as a false. एक तो ये क्या है पता नहीं. Come things work. Oh, okay, sorry. Oh, okay. I'm not sure if that has to do anything. Not sure, but oh, okay. Now we can see. So it says 1 2 3 4 5 छठा 1 2 3 4 5 6 0688 3 3 6 0688 ही तो है. मेरे को तो सेम में दिख रहा है भाई. इसको फॉल्स किधर दिख रहा है? It's saying that as a false. 2 3 2 2 3 8. I'm not sure. Okay, anyway, for the time being, let's stop it there. We'll see in the next iteration.